Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at acid-base titrations and titration curves. Now, more specifically, we're only going to be looking at strong acid, strong base titrations and titration curves. In lessons coming up in courses that go beyond this one, you will look at weak acids with strong bases and weak bases with strong acids, both monoprotic and polyprotic, which get much more complex. So this is the baseline understanding as we move forward to reach that more higher and difficult type of lesson. So first thing I should talk about really is, what is a titration? So a titration is when you react two solutions with one another. You will know the volumes of both and the concentration of one, and it's used to figure out the concentration of another. So this is used to figure out the concentration of an unknown solution by titrating it with a solution of a concentration you actually do know. Now, there's lots of ways you can know the concentration of what we would call the titrant. You might buy it that way, or you might make the solution by dilution or from solid in order to do that, which we've talked about in previous lessons. So essentially, we're trying to figure out the concentration of something we don't know. So on this page, I'm going to start talking about the basic titration equipment. Then we'll move on to reading a burette, and then we'll talk about a titration curve and how do you get a titration curve and how is it done. On the following pages, we'll look at actually doing some calculations and using stoichiometry to make a calculation of an unknown concentration. So let's start with our equipment first. All right, this very long piece of glassware, skinny piece of glassware, is called a burette. A burette usually measures the volume of a solution to 1/100th of a milliliter. Generally, we're plus or minus 0.05 milliliters on any of our readings. And this is where you would put something called the titrant. The titrant goes into the burette. And the whole point of doing the lab is really to record the volume of the titrant. That's going to allow us to understand or be able to make the calculation for our unknown concentration. Usually, not all the time, but usually we know the concentration of the titrant. That's usually the thing we do know. Now this thing over here is called a pipette. A pipette is accurate to, I believe, plus or minus 0.005 milliliters. It depends on how big the pipette is. So the ones at our school is 10.00 milliliters when you fill it up to this line here. And so the error would be plus or minus, sorry, I should move 1.5 over there, probably about 5/100ths of a milliliter, maybe a little bit less. Now, what goes in the pipette is called the sample. And usually we don't know the concentration of the sample, we just know its volume. So pipettes, again, they can come in all varieties of sizes. The most common would be 10 mil, but you can have 5, 15, 20, 25, 50. They can get quite large. Now what would happen is you would actually suck your sample up from, say, a beaker. So I'd have a beaker and I'd have this sample and I go, I don't know the concentration of this sample. And you would put a bulb on the top of the pipette and you'd squeeze it and then you'd stick it in the solution, and then the solution would go into the pipette and you'd fill it up to its fill line, and then you would know it's exactly 10 milliliters. And then you would transfer that solution into what is called an Erlenmeyer flask. Or most places around the world actually call it a conical flask, but an Erlenmeyer flask. And again, the Erlenmeyer flask would contain your sample. Now, sometimes you'd actually transfer into a beaker if you're using a pH probe. I'm going to talk about that in a minute. But I would use an Erlenmeyer flask if I was doing a titration and I was using a indicator. And really all I want to do is I want to get to an end point. I'm not actually recording pHs as I go. So we're going to talk about the two different ways of doing a titration, acid-base titration. This is kind of the second way we're going to look at it. Okay, so 3 pieces of equipment. The titrant goes inside of what we call the burette. The burette is very, very accurate at measuring volumes. It's within plus or minus usually 5/100ths of a milliliter. A pipette is actually usually a little bit more accurate. The pipette is used to get a very, very accurate volume for a sample. It's usually plus or minus. I believe it's actually smaller than 5/100ths of a milliliter. And what you would do is you get your sample in your pipette because it's very, very accurate, and then you would transfer that into an Erlenmeyer flask, which is very easy to use to swirl the solution as you do the titration. The other option is you can use a pipette and transfer it into a beaker, and then you would insert into the beaker a stirring rod, and that would go on a magnetic stirring apparatus, and it would do the stirring for you. You wouldn't have to swirl. That's not something we do at our school, but it's probably something you'll come across at university level. So that's the basic equipment. Now, when you do a titration, you have to be able to read the burette. So you have to be able to say what volume you started with, what volume you ended with, so that you can get a difference. And so then you would have a change in volume of your titrant. So what I'm going to do is I'm going to zoom in on a picture here. This is a picture of an initial volume and a final volume during a titration, just a random one, okay? Now, what I want to talk about too is it's kind of weird. When the burette is completely full all the way up here, the volume reads 0. When it's empty down here, it actually reads 50. This is so we can get values for us to fill into a chart that are easy to subtract. It's just the way a burette is set up. So essentially, where it says 0 here, this is at the very top of the burette almost. And so when we read a burette, we're always reading downwards, okay? So for instance, if I wanted to figure out this initial volume, I would start reading downwards, and I would notice that this line here, which is called the meniscus, it's the bending of the water, is below 1 but above 2. So what I would do is I'd say, all right, my volume is 1 point something something, because I'm reading down and I haven't reached 2 quite yet. Now, generally, you would use a little burette reading card, which would kind of highlight that curvature in that line and making it easier to read. And you should be able to kind of see a line going across your burette. And what you would do is you would read that line from the bottom of the meniscus like that. Okay, so I would go, all right, that's the bottom of my meniscus. And then I'd start reading down. So I'd go like this. This is 1.1, 2, 3, 4, 5, 6. And it's right on 6. So this is 1.6. And then because it's right on 6, this is going to be 0. This last digit here is generally either 0 or 5. You're either directly on a line or you're between lines. So for instance, I'm gonna put this in, I'm gonna delete it. Imagine the meniscus fell in between those two lines, not on the line. Then I would say that that was blank 5, and my last digit would be a 5. Sometimes you'll see questions where they say, oh, the volume was 1.62. I think it's a bit ridiculous to be able to tell the difference between 5/100ths and 2/100ths of a milliliter. Our eyes aren't that good, and it really depends on is your eyes level with the line and a whole other bunch of factors. So this last 100th spot generally is 0. if the meniscus lands right on a line, and 5 if it lands between 2 lines. Okay, so let's look at the next one. I'm going to make my line for my meniscus. I'm going to touch the bottom of it like this. Okay, there we go. It's right on a line. And then I'm going to read downwards. So reading down, my meniscus falls between 17 and 18. So I know that this is going to be 17 point something something. And then I'm going to count up how many notches I go down. So this is 17.1, 2, 3, 4, 5, 6, 7. So this is 7, and because it's right on a line, that's 7, 0. So then if I want to figure out my change in volume, what I would do is I'd take my final volume, 17.70, and I'd subtract away from it 1.60. And so we get 0, 1, 6, 1, and this would be in milliliters. So that would be my change in volume for this specific trial. So generally when we're dealing with acid-base titrations, there's kind of 2 different ways of doing them. One way is to just add an indicator to our sample and add solution from the titrant, from the burette as a titrant to this solution until the indicator changes color. So that's what we would do at our school. We would do 3 trials or 4 trials or 5 trials where we get a change in volume of what it took to change the indicator color of the solution, and then that we would use that information to calculate the concentration of our unknown. So that's one way of doing an acid-base titration, where your goal is simply just to get the concentration of your unknown. There's another way you can do it. It looks a little bit different. You would use a beaker in this spot here, and you would have a pH probe inside of that beaker, and that pH probe would give you an exact reading, and you can follow that reading as you're adding the solution to it. So it might say something like 1.00, 1.01, 1.20, and it would gradually get higher and higher and higher as you continue to add the solution if we were adding base to an acid. The goal of doing it that way would be to make something called a titration curve. So on the right here, this is called a titration curve. And what it is, it's a graph showing the pH of your sample. Okay, so the sample again is in the Erlenmeyer flask. It's of unknown concentration. And along the bottom is the volume of your titrant as you add it to the solution. And what you would do is you would essentially add a drop or 2 of your titrant to the Erlenmeyer flask or to the beaker, and then record the pH and record the change in volume. And you would continue to do this hundreds of times. Here is an example of a chart where somebody is going to make a titration curve from the data. Now, this data doesn't match this curve. It's just an example. So essentially what you would do is you put your pH probe in your sample and you'd record the pH. Okay, so before I added any solution, it's 3.4. Then I added a little bit of base. It went up a little bit. I added a little bit of base. It went up a little bit. I added a little bit of base. And you would do this no less than, honestly, probably 50 to 100 times. There would be a massive amount of data. And then you would take that data and you would plot it. So this curve here would represent a set of plotted data like this chart, and you would end up having dots kind of like this, and then they get really tightly packed together like that, and then you might have one here, 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 and then you'd have a whole bunch of plotted points coming out like this. And nowadays we would just generally do this in an Excel program. So you would have a computer open, it would record this data, then you would put it into a graph and it would generate a graph like this. So when I look at this specific graph, I know that this was the titration of a strong acid with a strong base. Okay, and I'll tell you why. First of all, whatever is being titrated, okay, so it says the titration of, this thing is the sample. Okay, and when I look at my graph starts at a pH of 1, which is telling me my sample is acidic. The fact that I'm below 7 and on my sample, that means my sample is an acid. Now, I can't titrate an acid with an acid, so therefore it's being titrated with a base. But what I want to talk about is how do I know that this is going to be a strong acid with a strong base? And that's all based around this. If we have an equivalence point, which is equal to 7, and if you look on the graph, this is at 7, then I know I have a strong acid being titrated with a strong base. And the reason for that is when you titrate a strong acid with a strong base, your products are going to be water, which is neutral, and a neutral ionic salt, which is neutral, and so your pH is going to be 7. So I know that this is the titration of a strong acid because when I look at the sample pH, it's acidic. Now I can't titrate an acid with an acid. I got to titrate it with a base. So I know that this is the titration of an acid with a base. And the reason why I know it's a strong acid with a strong base is because the equivalence point is at 7. When you do a strong reaction, you're always going to produce two things, a neutral ionic solution and water, both of which are going to be neutral. Now, if you're wondering, what is this equivalence point and how do I determine it? The equivalence point is when the concentration of one reactant is equivalent to the concentration of the other reactant. So the moles have canceled out completely. It is a mathematical figure. Now, if I have an exact same amount of acid and base, that's called neutralization. And when something is completely neutralized, its pH is going to be 7. So again, that supports that I know this is strong with strong. The other thing that supports it, or how we figure out where the equivalence point is on this chart, is essentially where this line starts to go up. Okay, so where this goes up and it flattens out, the equivalence point is roughly the middle of where it flattens out vertically. Okay, so if I was to make a little tick and say, all right, this is where it starts to go vertical, and this is where it starts to come out of vertical, and then I count up my squares. I go, okay, one above, one below, one above, one below, one above, one below, and then about 3/4 of a square, about 3/4, bang in the middle. So the distance between here and the distance between here is essentially equal. The middle of that point is called the equivalence point. Again, that's where the reactant concentrations are equal, and if you have a strong acid and a strong base, this is going to give you a pH of 7. Now, if you were to titrate a weak acid or a weak base with a strong acid or a strong base, the equivalence point would never be at 7. This is something that you will learn in acid-base equilibrium and will be explained to you at that time. For this course at this time, we will only be doing strong acids with strong bases, and the pH at the equivalence point will always be at 7 no matter what. Just if it's a strong acid being titrated, it starts acidic and goes up like this. If it's a strong base being titrated with a strong acid, it's just the inversion, which looks like this. Now we're going to look at two questions where we're going to make some calculations based off some data collected from a strong acid, strong base, or strong base, strong acid titration. So we're going to start with the first one, which is the titration of a strong acid with a strong base. So the way that this reads is that the strong acid is going to be the sample, because if you're titrated with a strong base, then your strong base is going to be the titrant. Okay, so we're using an indicator here, so there'll be no giant chart with 50 to 100 data points to plot. We just want to know what is the concentration of our strong acid when we hit what we would call the end point. So I'm going to talk about that just in a moment. I'm going to read the question first, though. So it says, calculate the concentration of 10 milliliters of HCl titrated with, and again, I have the concentration of my titrant titrated with 0.8 moles per liter sodium hydroxide. The volume recordings of the sodium hydroxide are recorded below. So they've done 4 different trials here. So to give you a better idea, I know this is difficult because you don't have the apparatus in front of you and this seems quite bizarre. I'm gonna try to draw it out for you, okay? So the fact that I have a 10 milliliter sample, and more specifically 10.00 milliliter sample of HCl, what that would mean is I would have used a 10 mil pipette. So this would be a 10.00 milliliter pipette to get my sample of HCl. So I would suck up 10 milliliters of HCl into this pipette, and so it would be filled up to a line, say about there. Okay, so this would all be filled with HCl. This would then be transferred into an Erlenmeyer flask. So this would be transferred over into an Erlenmeyer flask, and it would fill the bottom of that flask. Okay, so again, this would be the Erlenmeyer flask. This would be placed under a burette. Okay, and the burette would have something called a stopcock on it, which is a valve, and you're able to open and close the valve to allow the titrant to come out. So this would be the titrant, and the titrant here would be sodium hydroxide of known concentration, which is 0.80 moles per liter. And what we're trying to do is to get an average volume to reach our equivalence point. If we had that volume, and we have this volume, which is 10 milliliters, we would be able to figure out the concentration of our hydrochloric acid, which is ultimately our goal. So again, I transfer this in. I would read my burette. So the first trial, they read it as 0.80 to start. When the indicator changed color, I'm going to talk about that in a second, the person stopped the titration and the volume was 12.9. And then they would subtract those two values to get a volume for this trial. So if you subtract those, it's 12.10 milliliters. Okay, I want to talk about this endpoint a bit. Okay, so an endpoint, not equivalence point. An endpoint is when an indicator changes color. Okay. Now, you want your endpoint to happen very close to your equivalence point, which is going to have a pH equal to 7. So the equivalence point is mathematical. It is literally when the concentration of the two reactants is equal or very, very close to equal. The endpoint is when the indicator changes color, and you want the indicator to change color close to that equivalence point. So if you were to look at something to use as an indicator that changes color close to 7, probably the most common one used would be bromothymol blue. Okay, bromothymol blue has a range of 6.0 to 7.6, and it is yellow below 6 and it is blue above 7.6, and so the in-between color is green. Now, In between 6 and 7.6 also is the pH of 7. So what I would do is I would take my initial reading from my burette. I would slowly add the solution in, very slowly, and I would keep swirling and stirring this Erlenmeyer flask until the solution went from yellow, because we have acid in here, which is below 6, so it would start yellow, and then eventually it would turn green, and then I would stop the titration. Because now I know that I'm at my equivalence point. That's how I know my reaction is over. Then I record the final volume, I take the difference of the two, and that's the volume required to neutralize the titrant, or you can talk about it as being the other way. That's the amount of volume it took to neutralize the hydrochloric acid. So for strong acid, strong base, people either use bromothymol blue and they go for a green endpoint. So this, when it turns green, that would be the endpoint. The other one that's used quite a bit if you're doing this is phenolphthalein. It actually turns pink at 8.2, but to be honest, the difference between having this titration stop at 7 or 8.2 could be as little as 1 drop or even half of a drop. Okay, so that one's also used. We're going to stick with bromothymol blue though. Okay, so to recap, the end point is when an indicator, which is in the sample, changes color because we have a neutralization happening. An equivalence point is mathematical. It's where the concentrations of the reactants and products are equal. You want to pick an indicator whose midpoint color change, or where it changes color, is very close to your equivalence point. Bromothymol blue has a midpoint color of green right at a pH of 7, and so quite often it will be used in order to do this titration. So let's look at completing this question quantitatively and actually doing the calculations required to get a concentration. So let's finish by doing this. What you would do in the lab, you get your trials and you would calculate your changes in volume. So the first one was 12.10. If you do the next one, it's 11.30. The next one is 11.40. And then the last one is 11.20. Now, we always use our 3 best trials, and the general rule is they have to be within plus or minus 0.1 milliliters of one another. Sometimes we even go to plus or minus 0.05 milliliters. Now, if you want to know what that is in terms of like actual liquid, it's about a couple of drops. That's it. So this has to be done to a great degree of accuracy. So what you would do is you look at your values. You'd say, all right, these 3 here, if you consider 11.3 the middle point, up 0.1 is 0.4, down 0.1 is 0.2. Those are within the plus or minus 0.01 milliliters from your middle value. This first one is way off, and so I would throw this trial out and I wouldn't worry about it. Then you would have to average these volumes. So what I want to get is an average volume. So all I would have to do is go 11.30 plus 11.40 plus 11.20. Divide them by the number of trials, which is 3, and out would come 11.30 milliliters of NaOH. This is the volume I'm going to use in my stoichiometry. So now I need to write a balanced chemical reaction. So the balanced chemical reaction would be HCl aqueous plus NaOH aqueous, and this would produce HOH liquid, or H2O if you want to write it like that, and NaCl aqueous. So this supports the whole idea of the equivalence point being 7. Okay, so we have a strong acid and a strong base. If I have equal amounts of them, then I would have no reactants left. These would all be gone. So the only thing I'd have left in my Erlenmeyer flask are these 2. And of course, water has a pH of 7 when it's pure, and sodium chloride is a neutral ionic compound and it has a pH of 7. So again, that's why the equivalence point is at 7. So the whole goal of this, again, was to figure out the concentration of HCl. We know the concentration of NaOH at 0.80 moles per liter. The volume of the HCl is you get from your pipette, which was 10 milliliters. So this is 0.01000 liters. The volume here for the NaOH we calculated as the average volume. And so the average volume we calculated was 0.01130 liters, or 11.3 milliliters. Now, in order to compare one thing to the other, we have to do a mole-to-mole ratio. The way that this is balanced, though, is 1 to 1 to 1 to 1. So in order to do this calculation, we would simply take our concentration and volume of NaOH in our first step, calculate the moles. Then we can do a mole-to-mole ratio in the second step. And then in the third step, we can calculate our concentration. And so let's do that. I'm running out of room, but we'll fit it in. Okay, I'm going to start with step 1. So I'm starting with my number that has a single unit, so 0.01130 liters times. I want to get rid of liters, it has to go on the bottom. For every 1 liter of NaOH, it's 0.80 moles of NaOH. Okay, so the liters cancels out with the liters. Now I need to do my mole-to-mole ratio, which is nice and easy. It's 1 to 1. So I got 1 mole of NaOH for every 1 mole of HCl. So the unit of the mole of NaOH will cancel. Now I need this just in moles per liter. So I'm not looking to cancel this moles of HCl out. I'm leaving it. I just want to put it over liters. So the volume of the sample was 0.01000 liters. I'm going to put that in. So nothing else cancels. Everything on top, hit divide. Everything on the bottom, hit equals. And when I do that, I get an answer of 0.904 moles per liter. Now, if I look, I need 2 significant digits because of the 0.80 moles per liter. So my final answer would be this. The concentration of HCl is equal to 0.90 moles per liter. Now, what I'm going to do is I'm going to show you what a titration curve would look like this for this reaction. It's just going to be a rough sketch. This would be done with a pH meter, not with an indicator. And I'm going to call this a pH of 7. So this would be pH. This would be your volume of titrant. Okay. Now, the volume of the titrant at the equivalence point we determined was 11.3 milliliters. So let's just call this 5 milliliters. We'll call this 10. We'll call this 15. This is kind of just a sketch, okay? And so we would start with a very low pH. I don't know what it is, but it would be flat for a long time. So it would go flat, 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 flat. Then as we get close to 10, it's going to start to go almost completely vertical. I'm going to call this 11.3 milliliters. It's going to go straight up like that. And then 1, 2, 3, 4, 1, 2, 3, 4. And then it would go up and flatten out like this. So it would have an equivalence point equal to 7. The volume at that point here would be 11.30. And what you'll notice is as this starts to climb and become vertical, it would be there and there, and about halfway between those 2 points, we would find 7. And that's what the pH curve would look like for a strong acid being titrated with a strong base with only a couple of definite values. I know the volume is 11.3 at the equivalence point. I know the pH is 7, but I didn't know where it started or where it ended. This is just a rough sketch of what it would look like. So in this next question, we're just going to do the reverse. So instead of titrating a strong acid with a strong base, we're going to titrate a strong base with a strong acid. So again, when you're reading this, it says titration of a strong base. That means that this is the sample. With a strong acid, this is going to be the titrant. So it says calculate the concentration of KOH, that's my strong base, with 0.5 moles per liter hydrobromic acid. This is going to be my strong acid and my titrant. The volume recordings for the hydrobromic acid are in the chart below. These charts are always for the titrant, okay, always. So what I like to do here is we'll draw out the equipment. So I'll say, all right, we've got a burette, and we have an Erlenmeyer flask, okay, and we have a pipette, okay. I would like you, if you feel confident enough at this time, I would like you to state what solution goes into these different pieces of equipment. I would like you to calculate your average volumes, your volumes for each trial, and then get an average volume. Write a balanced net reaction and do the stoichiometry to solve for the unknown concentration of KOH. If you feel confident enough at this time, please pause the video and try the question. Now that you've had a chance to try the question, or if you didn't and you just want me to watch me do it, let's begin the process. So first of all, the titrant, which is in this chart, has to be in the burette. So in here we have HBr aqueous. Now I have 10 milliliters of KOH. So that's a really good indicator that I have a 10 milliliter pipette, and this contains the KOH. The KOH would then have to be transferred from the pipette into the Erlenmeyer flask, so I would have KOH in there. And again, I would use bromothymol blue, which changes color at 6.0 to 7.6. It's blue above 7.6, it's yellow below, and green in between. I'm looking for a green endpoint because my equivalence point should be very close to 7. Now, that means that this solution in the Erlenmeyer flask to start will be blue, and then it's going to turn to green. Now, if you did a really poor trial, it would go blue right to yellow, and you've skipped the equivalence point and the end point, and therefore the trial would be deemed useless. Okay, so we're looking to start blue and end green. All right, next, let's do our volumes. So the first one would be 12.50, and then we have 12.00, then we have 12.10, and then we have 12.00. And so there's 3 that look good here. That means I get rid of this one here. And so my average volume would be these 3 added together. I'll put that in brackets, and then I would divide by 3. Now, my volume average for the HBr would then be equal to 12.03 repeating milliliters. So on my diagram, I'm going to show you everything here. Okay, so I want to figure out the concentration of this. I know the volume is 10.00 milliliters. In the question, I was told the concentration of HBr was 0.50 moles per liter. I then carried out the titration lab. I got my 4 volumes. I've averaged them out, and that's given me an average volume of 12.03 repeating milliliters. Now I can start to proceed to answer my problems. Okay, so next step, balanced chemical reaction. So HBr aqueous plus KOH, double replacement, K replaces the H to give us KBr aqueous. Group 1 metal cation with a conjugate base of a strong acid, pH would be 7 of that. And then I have H and OH, or HOH, which is water, pure water, is going to be 7. My equivalence point is going to be at 7. Let's write down all of our information, known and unknown. So I'm trying to figure out the concentration of KOH. The volume from the sample, which is taken from the pipette, is 0.01000 liters. I need to figure out the moles. The concentration of the known titrant was 0.50 moles per liter. The volume was 0.01203 repeating liters. And I need to figure out the moles of that. All right, so step 1, take that concentration, turn it into moles. Step 2, mole to mole ratio. Step number 3, turn those moles into a concentration, and we're going to be there. So let's start with step number 1. Starting with my number that has a single unit in it, which is liters, 0.01203 liters times, I want to get rid of liters, that goes on top. I want moles, that goes on top, sorry. I want to get rid of liters, that goes on the bottom. I want moles, that goes on top, so that's HBr. There's 0.50 moles for every 1 liter. The liters cancel out like that. Okay, so that's step 1. I then have to do the mole to mole ratio. Now, this is a 1:1:1:1 ratio. So for every 1 mole of HBr, I have 1 mole of KOH. That's going to cancel out my units of moles of HBr. Now, I don't want to cancel out the moles of KOH. I just want to put it over liters. So I'm going to go 1 over the 10 milliliters, 0.01000 liters. No unit cancels out there. I take everything on top, I hit divide, everything on the bottom, I hit equals. And that gives me a concentration of 0.6015 moles per liter. I need 2 significant digits based on the 0.50 moles per liter in the question. So the concentration of my KOH would be 0.60 moles per liter. Now we'll just do a quick sketch of what this would look like. So here, this would be the pH of the sample, and down here, this would be the volume of the titrant. Again, the volume of the titrant would be the HBr. We'll call the middle 7, and we'll do the same thing. So 0 milliliters, 5, 10, 15, 20. So I know I'm starting as a base, so that's going to start up high. I'm not going to give it a value. The equivalence point has to be at 12 milliliters and 7, so about there. So I'm going to have flat, 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 flat. Then all of a sudden it's going to go quite vertical. And then it's going to come out flat, 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 like that. So the equivalence point is at 7. And the volume it took to get there was roughly, 12.03 is roughly there. And this is the general look of it. So the solution would be blue, 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 like this, okay, throughout this region because of the indicator. And then it would turn green in this area. So I would stop my titration there. And if I overshot the titration, then it would be yellow down there. And that's how the sample would look depending on if you stop this at the right time. So there was a lot to take in today. I do want to really push the fact that this is very important that you know how to look at a titration curve and understand what's going on. That's part of acid-base equilibrium as we continue down the road. The stoichiometry and the titration part of it is something you do in redox chemistry. It's just not with acids and bases. It's with oxidizing agents and reducing agents. And the stoichiometry still applies. The equipment still applies. So this is the first time we're looking at something very important, which is titrations, the equipment involved, the data collected, the stoichiometry, and interpreting pH curves. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.